Hello. Good evening, class. This is Dr. Emmanuel Ebwe, Professor of Business and Economic Statistics in the Department of Economics and Finance. Today, our class will be on normal distribution and confidence intervals. So I will share my screen so that we all can see. As I explained, this class is a high flex class, and the course, as we discussed last week, will focus on inferential statistics. And so today, we are going to begin our first lecture to lay the foundation for inferential statistics. As we said last week, when we are talking about inferential statistics, we are going to demonstrate, we're going to discuss the purpose of inferential statistics. In inferential statistics, we use information from a sample to make inferences about a population. For example, we ask ourselves, what is the average travel time for students that come to McGivers College? The population is every student in McGivers College, or every student that comes to school on a particular day. And so we ask ourselves, what was the average travel time for these students? When we ask that kind of a question, we may not be able to obtain the information from the entire population. If you have information from the population, then you have the true average. But if we don't have all the information, the population count, then we can only get a sample average. So we take information from a sample, say a sample of 30 students or 40 students, to make inferences about the characteristic of the population. So let us proceed and see how we go. All right. So today we're going to lay the foundation for inferential statistics, and we're going to begin from the normal probability distribution. For purposes of this class, the foundation of our understanding of inferential statistics will be from the normal probability distribution. Now, take note, the foundation for inferential statistics generally is probability distributions, but all probability distributions are not normal. We have different kinds of probability distributions, but for our purposes and at this level, we are going to rely on probability distribution. So in summary, again, the foundation for inferential statistics that we're going to study is normal probability distribution. We have our subject. Our subject is the population. Okay, so the population of students at McGivers College, the population of fish in a fish pond, the population of houses in a neighborhood, and you can go on and define your population. An objective is to describe the characteristics of the population, say average income, average travel time, average GPA. Other examples would include the average weight of fish in a fish pond. And so we use information from a sample size small n to make judgment or inference about the population. Now, as you can see, our learning objectives are very clear. For this lecture, we would try to describe the standard normal distribution and use it to calculate probabilities. We will compute and interpret a point estimate of a population. We will compute and interpret a confidence interval for a population, and we will compute and interpret a confidence interval for a population proportion. So the first one we will compute and interpret is a confidence interval for a population mean. Okay. So we begin by describing the characteristics of a normal probability distribution. Okay. Now, normal probability distribution presents the values of a random variable. Okay, an infinite set of values for a random variable. The normal probability distribution is a continuous probability distribution. It is not discrete. It is a continuous probability distribution. The normal probability distribution is bell-shaped and has a single peak at the center of the distribution. It is symmetrical about the mean. That is, the values of a variable that is normally distributed are distributed symmetrically about the mean. Now, it is asymptotic in the sense that the curve gets closer and closer to the x-axis, but never actually touches the x-axis. To put it another way, the tails of the curve extend indefinitely in both directions, and we will illustrate what that means. The location of a normal distribution is determined by the mean mu. Mu, the Greek letter mu, represents the mean. The dispersion or spread of the distribution is determined by the standard deviation sigma. Now, standard normal distribution, the values, please let's emphasize values. The values of a standard normal distribution has an arithmetic mean, a median, and a mode. And for the normal distribution, the mean, median, and mode are the same, they are equal. It is not necessarily so for other distributions. As a probability distribution, the area under the curve is defined to be 1, okay? And we will show what we mean. Because the distribution is symmetrical about the mean, half of the area under the normal curve is to the right of the mean, and the other half is to the left of the mean. So this is what we're talking about. As you can see, the normal distribution has a bell curve. The mean, median, and mode are smack in the middle. The area of the curve is 1. And so half of the curve has an area of 0.5, and half of the curve has an area of 0.5. All right. So now the question we ask ourselves is, when we look at this, we ask ourselves, how do we use this probability distribution to solve problems? Okay. So let me first of all say 0.5 of the area of the curve is on each side of the distribution. Okay. All right, so move to the next. And so now for a continuous probability distribution, you cannot find the probability distribution at a point. So you cannot find the probability of any value at a point. You have to find the probability of values in a range. For example, what is the probability that the random variable amount spent on lunch is between 6 and 8. You cannot find the probability that the amount spent on lunch is exactly 8 or exactly 6. but you can find the probability that the amount spent on lunch, which is your variable, is between 6 and 8. Or the amount, the travel time, for example, let us say travel time in minutes is between 15 and 25 minutes. You can have any number of examples, the probability or what percentage of the life of, say, a tire is between, say, 7,000 miles. So let's, between 7,000 miles and 15,000 miles. Okay. Life of a tire. We can provide lots of other examples. Then we can provide lots of other examples. All right. So now, as we said earlier, we're going to use the standard number distribution. So we have to, first of all, define the standard number distribution before we think about how to apply the standard number distribution. The example we provide here is, we provide examples of how we can apply the standard number distribution. But before we think about how to apply the standard number distribution, we also have to define the standard number distribution. As we said earlier, the standard number distribution is an imaginary, the distribution of an imaginary variable that's called z. And this imaginary variable has a mean of 0 and a standard deviation of 1. And so the standard number distribution very often is called the z distribution. Actually, it is the distribution of z values. Now, a z value is the signed distance between a selected value and some designated variable x, and the population mean mu divided by the population standard deviation. And so we have a formula for applying the standard number distribution of z equals x minus mu over sigma. And so, for example, we ask ourselves, what is the probability of z, the imaginary random variable, has a mean that this z is the imaginary random variable that has a mean equals to 0 and sigma equals to 1. So what is the probability, or what percentage of the values of z are between 0 and 1.3? Okay. Actually, between 0 and 1.3. Okay. And so if you use the table of number distribution, which we're going to bring up right away, we find out that the probability that z has a value between 0 and 1 is, first of all, let us find the probability that z has a value between 0 and 1. Okay, this is the standard number distribution table. Okay, so we're going to use it to read off. Okay, when you look at this, the probability that z has a value between 0 and 1 is 0.3413. Okay, so let us put it here. equal to 0.3413. Okay, so let us also find the probability that 0 is between -1 and z is between -1 and 0. Okay, now when you read off the values of z, which I'll pull up again, you have to ignore the sign. So as we say, the curve is symmetrical. Let's look at it again. The curve is symmetrical. And so the value of z, we ignore the sign. And so the probability that z is between 0 and 1 is also the probability that z is between 0 and -1. So this is equal to 0.3413. Okay. All right. So let us find the probability that z is between -1 and 1. -1 is less than z, less than 1. Okay, so when we look at this symmetrical distribution and pull up the table, we go from z to 1, which is 0.3413, but also from 0 to 1, and from 0 to -1. It's the same thing. We have 0.3413 on both sides, and so the answer will be 0.6826, because we're going from one side of the curve to the other side. Let's see if we can make this a little bigger. Okay, this is 0, so we are going from the left and going to the right. So we cross the 0 point in the middle. And so we can add the 2 because we're going from the left, we cross the middle point, and we'll go to the right. So let us find then that the probability that z is between 0 and 1.3. So we have z between 0 and 1.3 is 0.4032, and we can extend our example here. What is the probability, or what percentage of the values are between 0 less than z less than 1.3? Okay, from our reading is 0.4032. And what is the probability that z is between -1.3 and 1.3? So in that case, we'll find the probability that z is between 0 and 1.3 going to the right, and between 0 and -1.3 going to the left, which will be equal to 0.4032 plus 0.4032, which is equal to 0.8064. Now, this means that 80.64% of the values of Z are between minus 1.3 and 1.3. That is a positive 1.3. All right. And then we can take it from there and begin to think about applications. Or maybe let's do some other examples. What is the probability that Z is greater than 1.6? Okay. Now, we did say earlier that half of the values of Z are on the left side and half of the values of Z are on the right side. And so if you think about the curve that we have here, okay, and so if you take the point where we're asking for Z greater than 1.6. So we go to 1.6 somewhere on this curve, and then we ask ourselves, what is the probability that Z is to the right of 1.6? And we look at the table, look at 1.6, and the value is 0.4452. And since we are looking at what is left on the tail end, then this will be equal to 0.500 minus 0.4452, which is equal to 0.0548. 0.0548. All right. Okay, so let's take it from there and see if we can find some applications. These are all illustrations that support, or examples that support our illustrations earlier. Okay. Now, an example here will be the weekly incomes of a shift foremen in the glass industry follow the normal distribution with a mean of 1,000 and a standard deviation of 100. So we ask the question, what is the Z value for income? Let's call it X, okay, of a foreman who earns 1,100 for a week. What is the Z value for a foreman who earns $900 for the week? So the Z values will be calculated as follows. Okay, for the person that earns 1,100, the Z value will be calculated as 1,100 minus 1,000 over the standard deviation, which is 1.0. So I'm going to put up some other examples. Okay. For the person that, what is the Z value for a foreman that earns 790? 790 minus 1,000 divided by 100, which is minus 2.0. That is the Z value for a person that earns 790. Okay. Now, the z-value for somebody that earns 840 will be minus 1.6, and we can provide example upon example. Okay. So here we have a question here, an example that we can apply practically. The Leighton Tire and Rubber Company wishes to set a minimum mileage guarantee for its new tire. Now, tests reveal that the mean mileage from a sample from the population, the mean mileage is 67,900 with a standard deviation of 2,050 miles. And the distribution of miles follows a normal distribution. So the Leighton wants to set the minimum guaranteed mileage so that no more than 4% of the tires will have to be replaced. So no more than 4% of the tires would have to come back. So let us see how we can solve this. Okay. The company's example is that the average tire is 67,900 and the standard deviation is 2050. So the probability that a tire will last between 64,000 and 72,000 miles is another example. And so we calculate a z-value. Okay, we calculate a z-value. And the z-value here, the probability here will be 72,000 minus 67,900. All right. Okay, so z-value for 72,000 is 1.12, and the z-value for 64,000 is minus 2.78. And so we look up the probabilities, and we go back to our probability distribution table, and we find that 1.6 is 0.4452, and the other z-value z-value is minus 2.78. Oh, this is 1.12, not 1.6. Okay. So the area under the curve is equal to, let's look up what it is in the probability table, 1.12. We have 1.1, and then we have 2, which is 0.3686. So we write that down. Point 3686, 0.3686, you see here. And if we look up the area under the curve for a z-value of minus 2.78, which is on the left, but then we ignore the sign, it is 0.4973. And when we add the 2, then we see that the probability or the percentage of tires that have mileages between 64,000 and 72,000 is 86.59%. All right. So how do we then apply these concepts to inferential statistics? So let us apply to inferential statistics. And we're going to begin with confidence intervals. Okay, we're going to begin with confidence intervals. Now, what is our objective when we talk about confidence intervals? Okay, what is our objective? Okay. Now, when we are doing inferential statistics, I could say, unless you have the value of, unless you have information and data from the entire population, you don't know what the true average is. You don't know what the true mean is. And so our objective in inferential statistics is to use information from the sample to make inferences about the characteristic of the true population. And so what's the problem? We don't know what the average is, okay? For example, what is the average amount of money that a customer spends at lunch? We don't know what it is. Now, and we do not know the true population mean. So our objective is that we want to estimate the population mean, mu, using the sample mean x bar. We want to estimate the population mean, mu, using the sample mean x bar. So the sample mean, that is the average we obtain from the sample, is called the sample mean, and we designate it as x bar, and x with a bar on top of it. We don't use x bar and combine it with the z value to estimate a confidence interval for mu. Now, when we estimate a confidence interval for mu, what we're simply saying is that we don't know what the true mean is. That is the true value of the average. We don't know what it is. However, a confidence interval gives you a certain percentage confidence that the true mean value is between some lower value and some upper value. So that is what we try to estimate, okay? We use x bar to estimate mu, okay? Like I said, we're going to limit what we do here. We will not try to use a sample standard deviation to estimate the true standard deviation, but we might get to the point where we use a sample proportion to estimate the true proportion. And we will explain that if and when we get there. Okay. As I explained before, when you estimate a confidence interval, it's an estimate of a range of values constructed from a sample so that the population parameter mu is likely to occur within that range at a specified probability, which we'll call the confidence level. Therefore, the confidence interval is x bar, which we obtain as a sample, as a point estimate, plus or minus some margin of error. And that margin of error is z times sigma over root n, which is the standard deviation divided by the square root of the mean. Now, our best estimate of the unknown mean, the unknown population mean, is the corresponding sample statistics. Okay. Now, as an example, suppose we have the sample mean x bar equals to 45, 420. We'll call this a point estimate of an unknown population mean, and a sample standard deviation of 3,500. Now, we are to construct a 98% confidence interval for the income of, say, managers in an industry. We select a z-value for 98%, and we have a sample of n equals to 68. So we take a sample of 68 managers and use that information to estimate the mean. Okay, and so what we do is the z-value for 98% is 2.33. And so the confidence interval for the estimate of the salaries of managers here will be 45, 420 minus 2.33. Let me change the brackets here. Okay. And so we don't cause confusion. Put the brackets around that. All right. So we get the values inside here first, and then add to 45, 420. And so the answer will be that the confidence interval for the salaries of managers will be between 44,558 and 46,281. Okay. Now, these are just SPSS printouts, which we're not going to use SPSS here. So that ends the lecture for today. If you have questions when we come in on Thursday, September 16, please ask your questions, ask for clarifications so that we can understand things much better. And thank you for your time.